All right, we only have 3 lessons left. So this is the only other lesson from chapter 5, and then we'll have a couple lessons on integrals from chapter 6. That'll be next week. So next week is the last week of new material. I'll spend some time the following week doing some review for a final. I want to emphasize about the final, just like the other test, there is a practice test. The difference is it counts for extra credit. So you can get up to 4% added on to your overall grade. So like if you were to ace a practice test, yeah, you would get that. So that could be quite helpful if your overall grade is a borderline case. Okay. All right, get the screen share going. Okay. The previous lesson dealt with the natural logarithmic function and how to take derivatives involving that. Here we're going the opposite way. Its inverse is the natural exponential function. So I'll talk about that and how to take derivatives involving it, and then we'll get into the problems. All right. So the natural exponential function is e to the x. It is also sometimes written as expx. And I mentioned a number e last time. So it, like pi, it's a number that has a decimal expansion that goes on forever. It's an irrational number. And that is the base of the natural exponential function. And it's also the base of the natural logarithmic function. So it's related to the natural log function ln x by the following. They cancel each other out, just as squaring and square root cancel each other out. So e to the natural log of x is just x. And natural log of e to the x, which, as we saw last time, can be written this way as x natural log of e, because the exponent can be pulled down out here. That is also equal to x. So these functions used in either order bring you back to where you started at x. So the natural log of e is 1. Now, what we need to know here in this lesson is if you have a function involving the natural exponential function, how do you take its derivative? So here are the differentiation rules that apply to e to the x. So what's interesting about e to the x is it's its own derivative. So this function by a constant is the only function that is its own derivative, which makes it very useful for like solving equations involving derivatives. In other words, differential equations. Now, what we'll see here in this lesson is not necessarily just plain old e to the x, but maybe the exponential function with some other function as its exponent. So if I have e to the f of x, so f of x is serving as the exponent here, so you can think of it as e to the f of x. Then by using this rule, the derivative starts out being the same as the original function. But then you have to take into account the chain rule that, because here we have a function of a function. We have we have a function e to the x applied to f of x. So f of x is serving as the inner function here. So whenever you have that, a function of a function, you have to remember to multiply by the derivative of the inner function. So you'd have f prime of x out here. So the derivative of a natural exponential function is itself times the derivative of the exponent. And we're going to see many examples of that in the problems that follow. But here's a kind of function that pops up all the time. If your function is e to a constant times x, we're going to see a lot of that. Then when you take a derivative, you'll have first itself, and then you take the derivative of the exponent. Now, I want to emphasize here, c is a constant. So can anyone tell me after I've gotten this far, okay, I'm using this rule here. I'm not finished yet. What do I need to include here in this derivative to make it complete?
You have to multiply by the constant?
Yes, because that's the derivative of the exponent. Derivative of a constant times x is, by the coefficient rule, just that constant. So that would go here. And again, it doesn't matter because multiplication is commutative. I tend to write it, it's customary to write it this way, just the constant out front. I guess because it reads easier. But yeah, so this is going to happen all the time in several of these problems where you have to remember if it's e to a constant times x multiplied by the constant. Okay. So now we'll just dive into our problems here. So ironic that after I spent so much time emphasizing this case, that's not what we have here in this first problem. We have just a plain old e to the x. So what this problem calls for, several problems in this lesson call for taking the derivative and sometimes, like in this problem, the second derivative. Now, the first part of this, of course, that is very much familiar territory for you. And just using the power rule like you have so many times. And then when you go to take a derivative of minus 4 e to the x, well, the derivative of 4 e to the x is just 4 e to the x. Because if that constant factor 4 is just going to stay here, e to the x is its own derivative. So this is it. There's nothing else to do here except to clean up over here. And we wind up with 20x cubed for the first term. And then for the second step, we're just going to go through it again. We're going to take the derivative of this to get the second derivative of the original. Okay. So if I go ahead and repeat, well, all right, so here's what we have so far. Original function, first derivative. So can anyone tell me, based on what happened here, to get from f to f prime, what would f double prime be?
$60x squared minus 4 e to the x.
Yeah, so same thing. We're using a power rule over here. And then 4 e to the x, like I said before, is its own derivative. So we just go ahead and grind that out. And there you go. And since you're going to see problems like this, please keep track of which derivative a problem is asking for. As I mentioned, like on test 2, I saw cases where the problem asked for a second derivative, you only gave it the first. And I could tell from what work you did submit that you knew how to take derivatives, so don't throw away points like that. Okay, this problem is asking for the same thing. Now, to take the derivative of this, what will we have to use? Which
Product rule.
Yes, the product rule, because here we have a product of x to the fourth and e to the x. All right, so here's what what the product rule gives us is so here we have we keep a minus 6x to the fourth times the derivative of e to the x. Well, e to the x is its own derivative, so first term will just be the function itself, and then for the other term we take a derivative of minus 6x to the fourth, and here we just go ahead and use the power rule on that, and then the e to the x just stays there. And then when we clean things up, this is what we have in the end. Now, for the second step, taking a second derivative, again, really in both terms, you're going to need the product rule, although it's worth noting that since the first term here is exactly the same as the original function, then you know what you're going to get from this. So that's something that so an observation like that can okay. Start to do a little editing here. Okay, so here's our original function, here's a derivative, and then we go to use a product rule again. So taking derivative of this part, that gives us this, and we know that because that's exactly what we did up here. What's left is taking a derivative of this part, and the idea is the same, that we have 24x cubed times the derivative of e to the x, which is itself, and then we have plus a derivative of minus 24x cubed. That's done using a power rule, and then times e to the x. And when this happens, whenever you're taking the second derivative of a product, notice that these two terms are the same. You get like terms. That's something that always happens when you take a second derivative of a product. So we go ahead and clean up this term and then combine these two to get a coefficient of minus 48. And then cleaning up this term gives us a minus 72x squared e to the x right here. Okay. I'm going to add a little bit here. Just so you can see, if you go back and look at this later, how this is done. Like in the first derivative, it's for e to the x prime plus minus 6x to the 4 prime times e to the x. So remember how a product rule works. You take your product and you have two terms. In each term, one of the factors in the product is differentiated, the other is left alone. So first term is e to the x, it gets differentiated, but that just gives you itself. In the second term, whatever polynomial you'll have, that is differentiated, and that's what gives us this here. And the same idea was applied down here to take a derivative of this to get these two terms, and then a derivative of this to get these two. Any questions about this one? Okay. Here it's asking for a derivative again. Your function is labeled y, so a derivative will be y prime. And then it's asking for a slope. Now the slope is the derivative at a certain point. And this is rather strange notation here of a vertical bar. What this says is you're going to, after you get the derivative of y prime, you're going to evaluate it at x equal minus 4. So you're going to plug in x equal minus 4 into your derivative after you get it. All right, so here we need the chain rule, because we have e to a function is 2x cubed plus 8. And in the course of taking derivative of that, as part of a chain rule, of course, we're going to need the power rule. All right, so here's our original function. So then y prime, because this is an exponential function, you're going to have itself times the derivative of the exponent. That's why I have a prime here. Then you have to work this out, and then you'll be done with getting the derivative. So what's done here is just using a power rule on the 2x cubed, and of course derivative of 8, that would give us 0. So then, after taking a derivative of that is complete, then we have a derivative. It's just a bit of a mess. So we need to combine all the constants. So first we clean this up a little bit. So then we have this. So this whole thing condenses to 6x squared. And then we have these constants here. We might as well combine these. And again, it's customary to move the x squared out to the front. So it's 36x squared times this exponential. So that's the first part of the problem, getting y prime. Now we need the slope at x equal minus 4. So now we substitute x equal minus 4 into this expression. All right, so here's throw in minus 4 here. Don't forget this is squared, so the minus is going to go away. But here it's cubed, so it will not. So we have 36 times 16, which would give us 576. And then once the exponent is worked out, minus 4 cubed is minus 64. So then we have e to the minus 128 plus 8, so we get e to the minus 120. This is the answer you would actually enter into Hawks using its keypad to handle like this exponent and so forth. So you would not evaluate this on your calculator. It's not asking for any number of decimal places. It just wants this expression. I should mention that e to the minus 120 is an extremely small number anyway. It's on the order of 10 to the minus 53. Right. Here's the kind of problem that you've already seen for other functions, but now we're going to carry out for an exponential. Take a derivative and then find out where the function is increasing or decreasing. So just like in the previous problem, we're going to use the power rule. Actually, we won't need the power rule for this. The coefficient rule is more appropriate because we have just x to the first power. So the derivative of this exponential function would be itself times the derivative of the exponent. So then you go ahead and carry out that differentiation. Derivative of this is just going to be minus 0.2. So we'll just multiply by that out front, and there is the derivative. Now, normally when you are asked to determine where a function is increasing or decreasing, you've gone ahead and gotten the derivative. What do you do with it next?
You set it to 0.
Yeah, you define any critical values, see where it's equals 0, and then everywhere else would be all positive or negative. But it turns out there's really nothing to do here because there actually is no solution. And the reason why is the exponential function is never equal to 0. In fact, it's strictly positive. So this derivative, all right, so this part, e to anything, it doesn't matter what the exponent is. Even this exponent, that's negative. E to anything, always positive. And then it's multiplied by this negative constant. So this derivative is always strictly negative for all x. So it's never. So there are no critical values. So what that means is the function is either always increasing or always decreasing, depending on whether derivative is positive or negative. And you can always plug in a value for x. So for example, if you were to plug in x equal 2, and then you'd be evaluating that. So you get minus 0.2 e to the minus 4.4. You work it out in your calculator and you get a negative value. So so a function is decreasing. Now you don't even really have to do this because, as I just mentioned, the derivative is always negative, just because e to anything is positive. So so you can conclude for that reason that the function is always decreasing. And this part is not actually necessary, but I just want to show you what the function looks like. Let's see where to go. Oh, wait, there's an error here. Oh, okay, never mind. Oh, there's supposed to be a graph. It's not showing here for some reason. Let's see. Sometimes it puts figures in strange places, but I guess it's not going to show it to me at all. Okay, but when I post the notes in Canvas, you'll see it there. But it's a function that is, if it behaves like this, it's decreasing and it's concave up. Because if I were to take the derivative of this, I would end up getting something positive. So that's why it's always concave up. Okay, so your answer is that where you would you actually enter the Hawks? Is the interval minus infinity to infinity. Okay, I guess this is where we'll be putting a graph if it wanted to show it, but apparently it doesn't want to. I'd make one last ditched effort to try to put that in there. Okay. This problem is a real quickie. All it's asking for is the derivative, and it's not too different than what we've seen. Actually, it's very similar to the very first problem. That we're just using a power rule for the first term. That would just give us 10x, and then 5 e to the x is its own derivative. So nothing to see here, really. That's okay. We have other problems that are more of a pain. Okay. This one slightly more. I believe it was the second problem we looked at. This is one that would require the product rule. So what the product rule would give sorry, I can't seem to type today, is going to have 5x to the fourth, so the first item in your product, times the derivative of e to the x plus derivative of 5x to the fourth times e to the x. And the result of that, so this stays as is, derivative of e to the x is itself. And then over here, derivative of 5x to the fourth would be 20x cubed. And then the e to the x would just be carried down. So then when you clean all that up, then this is what you get. Now, with problems like these, where your answer has multiple terms, if you get at least some of the terms correct, but not all of them, then that is good for partial credit. But again, try not to give those points away because there's plenty of other problems that have like a word problems that are more of a challenge than this. Okay, this is similar to another one of the earlier problems. It's just using different notation. Here, you take the derivative, and then you're supposed to plug in x equal -3 to find the slope of the curve at that particular point. Now, unlike previous problems, this one is going to require the quotient rule. Okay. Now, what that would give you in the numerator, you'd have the original denominator times the derivative of a numerator minus the numerator times the derivative of a denominator all over the denominator squared. All right, so that's your framework for your answer. Now it's just a matter of working out whatever derivatives appear in here. But the derivative of 4e to the x is just going to be itself. And then for this part, derivative of minus e to the x also itself, and then the 5 would not contribute anything. So now you wind up with this. And then this is just a matter of distributing everything to simplify, which is not really necessary. Well, actually, it is helpful for this problem because once a derivative is complete, you have to substitute x equal -3. So it is worthwhile to simplify this if you can, just so that you have less to do when you go to plug in that x value. Now, if I go to distribute, so I have distributing a 4e to the x through here. So if I have minus e to the x times 4e to the x, I'll have a -4, but e to the x times e to the x is e to the 2x. Why? Because laws of exponents. Here we have the same base, e, and you're multiplying them together. That means you add the exponents. So this is something you're familiar with from other types of problems. The exact same thing applies here. And then I have plus 20 e to the x. And then over here, same thing. I have minus a -4, so plus 4, e to the x times e to the x. You can think of it as e to the x squared also, but here too you would multiply these exponents, and that would give you, again, e to the 2x all over the same denominator squared. We're not doing anything with that. Right, something went very wrong here. Okay. And what we see here, these two terms, the first and last ones, cancel, and you are left with this. So now you're in a position to go ahead and plug in x equal -3 to find the slope of a tangent line or the slope of a curve at that point. All right, so here's what you're substituting into. And here we're now we're not asking for like a number rounded to a certain number of decimal places. If they are, but they would say so. But it's this expression. Again, with the assistance of Hawk's keypad, is what you would enter into Hawk's. Okay. Here we have an application problem. We have this function that describes how population of bacteria changes over time. Population growth often involves exponential functions. So what's happening here is here we have a exponential function with a negative exponent. So that's actually going to decrease as time moves forward, because x refers to hours after the experiment begins. So this denominator is going to be decreasing, but because it's in a denominator, the overall fraction is going to get larger. So in other words, the population is going to grow over time. So what the problem is asking for is, okay, how fast the population changing after 2 hours? So in terms of this function n of x, can anyone tell me, when it says how fast is the population changing at the end of 2 hours, what is it that this problem is actually wanting us to compute in terms of this function n?
The rate of change.
Which is?
The derivative.
Yeah. And then at x equal 2. So n prime of 2 is what it's asking for. Okay. All right, so yeah, so that's what we're after here. So then to take a derivative, there's two ways to go about it. What I'll show you here is the quotient rule. I need to fix the parentheses in here. All right, so bottom times the derivative of a top, but a top is a constant, so its derivative is 0. So therefore, this whole term will just go away. And what's left here is you have minus, and then top times the derivative of a bottom. When you take a derivative of a bottom, of course, a 1 would give you nothing. And then you have this function, 19 e to the minus 0.3x. And then times the derivative of the exponent, which is minus 0.3. So I'm going to add an intermediate step here, or 2. All right, so this is just what the quotient rule gives us. Bottom times derivative of top minus top times derivative of bottom. And then as that is worked out, you get just so you can see where everything comes from. 0 from taking derivative of 1 plus 19 e to the minus 0.3x times the derivative of the exponent, which is minus 0.3. So then, because of this, like I said, this term will go away. Okay. So then 19 times minus 0.3, that's minus 5.7. So that's where that comes from. So now all that's left is to just multiply out these constants. And what that gives you, so minus 2,000 times minus 5.7, that's 11,400 times its exponential. And now you're done with the derivative, at least. And what's required now is to substitute in x equal 2, equal to population rate of change at the end of 2 hours, and then round to a whole number. Okay, so we'll just set x equal 2 here, and then you're just gonna go at it with your calculator, and we get 47.9, but it requires a whole number, so we just round to 48. So after 2 hours, the population of bacteria is increasing at a rate of 48 bacteria per hour. Three problems left. This one another quickie where you're needing the chain rule because you have this exponential function with another function as the exponent. So the y prime turns out to be, okay, minus 2 just sits there. Then the exponential times the derivative of the exponent. So then when you go to do that, that's just using a power rule, derivative of x squared being 2x. So then we have minus 2, 2, and 2x. All of that needs to be multiplied, and that gives us minus 8x times this exponential. And this is a problem that was type of problem that was first seen in lesson 3.5, finding the absolute extreme or absolute max and min of a function on a given interval. So here the interval is minus 1 to 5 of this function, and rounded to 4 decimal places. So where can the absolute max or min occur? It can occur either at the endpoints, minus 1 and 5, or if there are any critical values in between. And again, this is an issue in test 2. They must be inside this interval to be considered. So first we need the derivative. So for this we use the product rule. I'll fill in some intermediate steps here. So we have 5x cubed times the derivative of its exponential plus derivative of 5x cubed times just the exponential. Okay. Then working out those derivatives, here we take the derivative of the exponent, which is going to give us a factor of minus 0.7 plus a derivative of 5x cubed, that would be 15x squared, and then times this exponential. So then we to clean this up, we have 5 times minus 0.7, so that's minus 3.5, the exponential, and then this x cubed. Actually, I'm going to move the x cubed over here, just because it's how these things are normally written. Okay. All right, so there we have the derivative. We have to find out where it's equal to 0, though, and it looks like it's going to be kind of a pain. But one thing that is helpful, and this often happens with exponential functions, is that when you have an exponential function involved, you're taking a derivative, generally every single term involves that same exponential function. And what that means is you can factor it out. All right, so here we have that same derivative set equal to 0. So if anyone want to factor out anything that you can anyone tell me what do we have that's common to these terms that can be factored out?
Would it be x squared e to the
0.7? Yeah, so I mentioned the exponential earlier, but yeah, we have each term has at least an x squared. So we go ahead and factor out the x squared. And this is what's left, minus 3.5 times the remaining x. And here we have just a plus 15. So now we need to see where any of these factors are equal to 0. Now, this part, remember, the exponential function is never 0, so you can forget that. Here we have x squared, so that'll be 0 when x is 0, so that's one critical value. And then you set this equal to 0 also, and what you end up with is so we get 0 from over here, and then setting this equal to 0 gives us 30 over 7. So these are two critical values. Now, check the interval, minus 1 to 5. Both of these lie within this interval, because 30 over 7 is going to be like 4.28. Yeah, 4.285. So it's in this range. So now we have 4 candidates for max and min: minus 1, 5, 0, and 30 over 7. So these are just in order from left to right. These are the x values we need to substitute into the original function. And so largest one is the absolute max, smallest value is the absolute min. And this is something that you would use your calculator for. All right, so what is it complaining about? Okay. So f of minus 1. Oh, sorry, g. We called the function g. So the original function is 5x cubed e to the minus 0.7x. So 5 minus 1 cubed e to the minus 0.7 times minus 1. So you need to, so that'd be minus 15, I'm sorry, minus 5 e to the plus 0.7. And what you get, let's see, they ask for 4 decimal places. So what you end up with is minus 10, 0.0688 when after rounding. All right, but we don't really know anything about this, as far as max and min, until we substitute in all of the values. So with 0 being the next point, well, from this 0 sitting out here, we're going to get 0. Okay. And then we have g of 30 over 7. So we're going to substitute 30 over 7 into the same expression. I'll just cut to the chase here. We get 19.5955. And then finally, g of 5 turns out to be 18.8734. So we see which is the largest, which is the smallest. So this is the largest value. So the absolute maximum And remember, it's an ordered pair. X value. I'll express this as so 30 over 7 is 4.2857. So it should be expressed that way. And the absolute minimum is at this point. It's the only negative value of the bunch. So -1 is the X value. And then minus 10.0688 is the Y value. Okay, so we have a business application like we've seen elsewhere. Here we have the demand function for products. So this is the price at which it's sold, but now it's an exponential function. And here we have this domain x between 0 and 75. And if you're trying to find the number of units, so that's x, it gives maximum revenue. And round to a whole number. So we need the revenue function. So you have to remember, for revenue, we have to multiply this by x. So here we have price per unit times x is the number of units. That equals the total revenue. All right, so then we just fill in what the demand function is here. And so, and just the way it's customarily written, not a big deal, but this is the revenue function. So now for derivative, we need the product rule. And just to show where all this comes from. All right, so we have 150x times the derivative of the exponential part plus derivative of 150x times the exponential. And then we take the derivative of that. Then we have the exponential times the derivative of the exponent, and that's going to be minus 0.1. And over here, the derivative will just be 150, and then the exponential. Okay. So then I have 150 times minus 0.1, and that gives us minus 15, x, and then the exponential, and then I have this other term here that was worked out. So this is the derivative of the revenue function, also known as marginal revenue. Okay. All right. So now we're looking for a maximum. So we set that equal to 0. All right. So, oh, missing a minus here. Okay. And we can proceed like in the previous problem, where you can factor out some things. So certainly you can factor out a minus 15, and you can also factor out the exponential. It's always going to be the same in whichever terms you have. And then what's left? Well, here we have just x. And then because I factored out a minus 15, it gives me a minus here. And then I factored out a 15 from 150, so that leaves you 10. Whoops. All right. This part is just a constant and an exponential. That is never 0. So then you set this equals 0, and we get 10. So that is the one and only critical value that we have. So that's the answer to the first part. When x is equal to 10, that's where revenue is maximized. Now, what you need to do for the second step is price per unit at maximum revenue. So the x value that you got, so 10 units, you're going to substitute that into your demand function, or your price function. So it's going to go ahead and compute d of 10. As a reminder, this is what d of x is. Substitute x equal 10 into that. And when you work it on your calculator, you get 55 point, et cetera, So rounded to 2 decimal places, we get $55.18 is what will give maximum revenue. So in other words, the most revenue that you could hope for under circumstances is this times 10 units, so $550 or $551, and from here 82 cents. So you're doing kind of problems that you've done in prior lessons, except now involving exponential functions. So just have to remember how to take derivatives of those. Derivative of any exponential function is always itself times the derivative of the exponent. So that's the main new item for this lesson. And also what comes into play, like when finding out whether a derivative is equal to 0, remember that an exponential function is never 0. And in most cases, especially those involving like a product rule, the exponential is something that you can factor out. So you have this messy derivative, but then you find, oh, you can at least ignore that part of it and focus on the rest, and then hopefully the algebra is not so bad from there. So, are there any questions about the problems that we've seen here? You're just waiting for me to let the 10 seconds of awkward silence pass. Okay. Well, then we are done for today. So I'll stop the recording here. If anyone has questions, they can stick around. Otherwise, scram.